All right, let's take a moment to refresh our memory about fundamental electrical constants. So, just like we've talked about before, current is simply the flow of charges. How much charge goes past in how much time. And that's easy to imagine. It's relatively easy to imagine that you could blow a wire up to approximately your size and you could see how fast the charges are running past you. Voltage is a little more difficult because potential difference is harder to imagine. You can do a little bit by imagining, for example, a vertical drop. You know, the greater the drop, the faster it'll be going at the bottom. But that's not actually that useful as a way of imagining current and electricity and the movement of electrical charges, because they're not accelerating under the influence of gravity. And so the idea of potential difference, I think, is actually really useful. The idea that voltage is the change in energy per charge. So if you look around a circuit and you see how much potential energy has been converted to electrical energy and how much charge has been moved, well, then you can work out what the voltage must have been. So this is actually a really useful way of thinking about the movement of charges. They go around the circuit exchanging their electrical potential energy for other types of energy. How much charge for each piece of charge. And the last one, resistance. Well, resistance is something that changes electrical energy to another form. It's anything. Wires are resistors. And as we're going to see, resistance is everywhere in a circuit. So Ohm's law is a very simple way of connecting together V and I and R. So simple, in fact, that we can just write V equals IR. Now, you can also imagine it in terms of the current flow, and this is a good way to kind of conceptualize it in your head, that if we write instead I shouldn't have chosen a better pen. If we think of it instead in terms of I equals V over R. So we know already I is how many charges are flowing every second. And we can see that if we know how much energy is available in the circuit, what the potential difference is, then how fast they can flow depends on how well they can get through the circuit. If they're spending their time hanging out, converting their electrical energy to other forms of energy, you can see that the current's going to be smaller. And I think that's quite a useful way of thinking about Ohm's law. Yeah, V equals IR, how fast the currents flow, times by how much resistance there is. But this one here is a more instinctive understanding. So if we move on to, I just mentioned it a little minute ago, the idea of internal resistance. The idea that inside something like a battery, there is a little bit of resistance. There is a little bit of energy exchange taking place. And you can test this for yourself by just connecting a wire across a battery. Now, if there was no resistance inside the battery, then I equals V over R would tell us that, it's going to be an infinite current that flows. You would expect the wire to burn through, but it doesn't. So there must be something inside the battery that's using up that electrical energy, and we call that internal resistance. So what we do is sometimes, now that we're in level 3 and we're like, more amazing, we will write our batteries like this. There's our little battery, and here's a little R. And usually, I hope you're not going cross-eyed looking at it. Usually we draw a little dashed or dotted box around it to show that's the inside of our battery pack, the inside of our power supply. It's got something that generates a potential difference, and it's got something that uses up that electrical energy, this little R, okay? And that little R, it varies battery by battery, and we have to, now that we're in level 3, we have to account for that when we're looking at formulas. So if you take the potential difference across the terminals of a voltage source where nothing is flowing, you'll get a certain value from it called the EMF, or electromotive force. And it has the symbol curly E, an epsilon symbol. So EMF, electromotive force, is another way of thinking about voltage. And I hope this is actually easier to understand. It explicitly talks about the force of the system, how fast or how hard it's pushing those charges around that circuit. And what we can find is that the V that we talk about, okay, that's not quite, and so sometimes you'll see your little formulas, you'll see them done like this, okay, and we talk about V and EMF, and we can say, well, actually, if we look around our circuit, we'll get a certain V voltage, and it's equal to the EMF minus the current that flows for whatever our circuit is, times by little r. Sometimes we're looking for little r, sometimes we're looking for the EMF. There's various things that we can do with this concept, but the really important one for you to get right now is that inside any power supply, there's a small amount of internal resistance. How big it is depends on the type of battery or the type of power supply it is. And we have this idea of EMF, yeah? The actual potential difference supplied by that terminal, some of which gets used up here by the voltage drop across little r, and some of which can be seen on the outside, on the terminals of our battery or power supply.